when we first thought about this session, and it was basically Yetka's initiative, she said, oh, we need to show everybody what Snap is about, like what makes it special when they use other programming languages in school. And we've got like a bunch of things that we'd love to show you and that we'd love you to use. So we'd like to start up with something that we could maybe all do together. So if you could get out your laptops if you want. If you don't, you can just follow along and maybe are a little bored. The thing that we'd like to start with is something that maybe shows a little bit of kind of why we're designing Snap the way we're designing it, and also what are the kind of important things that we like to do. Now, one of the things that when you start Snap, when you use Snap, that is very important to us is that it's not just a programming language. Don't worry, we're going to be hardcore nerding out soon. But it's also an environment that lets you interact with the environment around you. And this is something we often call physical computing, and usually physical computing is something that involves microprocessors, LEDs, some soldering, which is all great. But sometimes, like when you're in school, when you're in class, or when you're just sitting around in your chair, all you have is your laptop. And one thing that we like to remind you all is that your laptop is also a physical device, and it also has capacities to connect to your environment. And it has sensors, and it has pretty cool sensors. You all know my favorite sensors are the camera and the microphone. And part of what I love about the microphone is, like even more than using pictures, is first of all, it's safer to use with kids because it's easier kind of to share projects that might have voices in them than pictures. But also the kind of media that we're recording using Snap's microphone is a single list of samples, which makes it way easier to work with this data than if we're having kind of two channels of stereo sound. But I'd like to start out with just exploring a little something, and this and just recording something. And usually when we do this, we ask kids and folks to stand up and find something that sounds musical. Now, this is not musical. That's just a thud. You can make music. Of course, percussion is music. Problem is, you'll mostly find percussive sounds if you go hunting for this now. So we should have brought a bag of stuff that makes interesting sounds. So for the lack of interesting sounds, you can also just whistle or sing something. For the males among you, working with low and deep sounds is a little bit hard. It's better to have your Mickey Mouse voice or to whistle. So I'm going to say, snap, snap. Okay. So this is like my sound. You can get your own sound or your name, or you can whistle or do something. Folks, if you do this with kids in your classroom, it'll be murder and mayhem, because everything is going to erupt, you know, in joyful clamor, and you're never going to. So what you tell them is, everybody, believe it or not, well, of course not me, every of these kids, and I know because I've got two kids of my own, they never use these things, but they come with every of their phones. They actually do have headsets, believe it or not, even though they never use them. So tell them to bring their headsets. These have microphones, and then they can use these headsets, and it's way easier to do this without interfering with other kids. Since you're all adults, you can do this responsibly now and record 1 or 2 or 3 sounds in Snap. And you can play them back and okay, good. So, and then we're going to do stuff with that. Okay, wait. Okay, oh gosh, teacher Jens. I've just heard like five, like a melody. Folks, just one note, just one tone. Okay, got sound, everybody? Awesome. So what you can do with sounds in Snap is you can play them. In the sound category, there's a play sound block. You can select your sound, it's called recording. You can go to the, if you've got several, you can right click on this and rename this. I'm going to call it not recording, but I'm going to call mine Snap. But never mind, you could just, and you can then kind of select it, you can play it back by clicking on it. This is kind of fun. You can use loops. Well, you know you can do all of this, but this is just recording and playing back. Now the interesting thing is interacting with media, and also then playing it back, which kind of plows it back into the real world. So for this, check out this. This other block of this, the second category, in the second group down here, which says play sound ad, and then there's a big number at 44,100. And if I use this, snap, it sounds the same. And so I was just going to prompt you to try other numbers in there. So there's a menu that suggests some, but you can type in your own ones and see what happens. Okay, this is the one we know, like, play a little bit around with this. It's even more Mickey Mouse. Okay. You're not kids. I don't have to kind of, wow, what just happened? Anybody care to explain something you immediately notice about this?
The pitches.
The pitches, right. So a higher number gives you Mickey Mouse voice. The lower number gives you a giant's voice. And there are some numbers that don't give you any voice, that kind of you don't hear anything. So the pitch is different. Anything else is different?
You say
The speed, like it takes like the giant slower. Okay. So what's happening? How is that the case? It says at some hertz. So what's happening here is a sound. We can look at sounds. We can look at the samples of a sound. And we see that the samples of a sound, snap, is a bunch of numbers. It all starts with zeros because as I was pressing the button, I wasn't saying anything. I wasn't seeing snap yet. But, it's an awful lot of numbers. When I scroll down, there's numbers. And so these numbers are signals. They're the signals that are given to a membrane. Like when I speak into this microphone, there's a membrane that kind of gets pushed towards or away from a magnet. And that's the signal that gets recorded by the computer. And when you play it back, it's kind of the reverse thing. You put voltage into to a magnet, which again kind of repels or attracts the membrane in my speaker, which gets the air pressure moving, which gets your eardrums. And if you do this faster, if you increase the speed, these signals get processed faster, and it gets slower and faster. If you do it faster, the pitch increases. So hey, so if this is how it works, and we can put in different numbers, is there a correlation between these numbers? Like if I do 44,100 and I do the giant's voice, anybody notice a correlation between these two numbers? It's half the number that half the big number I'm putting in here is half the pitch, right? And double the number is obviously double the pitch. Hey, if that is the case, we should be able to use the number in here to make music with our recording. We should be able to maybe play a scale or a song with just recording one thing. Any ideas how we could do this, or would you like to try this maybe now? How about I give everybody like 5 minutes to play a little bit around with turning this into something that sounds like music, which is the hello world of media computation. Okay, try hello world of media computation. And have fun. Don't be shy. So you could use some suggestions. You could use like the for each loop. You could use or you could use the for loop. Maybe the for loop is even nicer. You might want to use some math blocks to make music. Maybe even some funky ones. Are there any musicians among us? Nobody dares to. Yeah, okay. Okay, one thing you might also want to do is a very handy block to use is the rest for beats block. Because otherwise you're playing them all at the same time. It's a little hard to come up with something that makes sense, right? So what I've tried is, anybody know, like, tell me, what's the usual kind of amount of, well, I've shown you. When we have an octave, which is the exact doubling of a pitch, we say octave, which is a funny way of saying 12, because it implies 8. But actually it's kind of 12 halftone steps. So we could think that, that we just take the numbers 1 to 12 and we multiply them by kind of one of these big numbers. So now we get kind of different frequencies and we could just play them back, and this should probably span an octave. And I'm going to try this and see what happens. That wasn't too great, right? Yeah. So any other idea? Or maybe I have to wait. Maybe 1 to 2 divided by 12. Could that be something? Any other idea? I'm desperately trying to come up with wrong answers.
It doubles in 12 steps, exactly. 6 steps. That's good. Square root 3.
Good point. So turns out this is one of the great things where you can actually teach kids and adults a mathematical formula. The mathematical formula was invented at the same time in China and in the Netherlands. In China, it was Zhu Xiaoyu, and I keep mispronouncing his name. Whenever I tell my Chinese friends that, well, I'm a big fan of Zhu Xiaoyu, they say, Zhu who? Germans, there is even a center where they keep track of Zhu's writings about this. He was a Chinese prince that experimented with the flute to find out pitches. And you'd think that Chinese music is kind of fundamentally different from Western music. It wasn't. That's also interesting. He was trying to find out the exact same halftone steps. And he was kind of one of the first ones to actually compute them using Indian decimal numbers down to the 24th digit and got it right. And at the same time, some Dutchman who was born Belgian, Simon Stevin, did the same thing. He translated mathematics into Dutch, and his claim was that Dutch is the best language for teaching mathematics because it's full of monosyllabic things. And most of the non-English words that we use in many parts of Europe today to talk about mathematics are actually from Simus 7. Like when in German we say mal nehmen, that's Steven. That's his word. He didn't say multiplication or something because he wanted to speak like people speak. And his passion also was many things. It's crazy. You got to Google Steven. He's one of these people, like, he built the first wind-powered racing car for the Prince of Orange. He's the guy who saw those windmills, and he was in charge of kind of the polders, and he came up with a way to increase their efficiency by a factor of 2 or 3. And he built fortifications, and he also wrote kind of the quintessential book about music, and came up with this way of really equal temperament scale of what it's called. And his idea was, never mind what the old Greeks said about harmonies being kind of, very equal relationships between numbers. Let's just divide an octave into 12 equally sounding steps, and that's just the 12th root of 2, which we could express by saying, this is just 2 to the power of a note divided by 12. And so what we should be able to do is we take the numbers from, let's say, 1 to 12. We take this. Now we've got these, we've got a whole octave, and we could just multiply that with like 44,100. Now we should be getting frequencies, and gosh, I should be prepared, right? Let's see how that sounds. Okay, so we got an octave. So this is the formula, how we can make music.
Except you should start with numbers from 0.
Maybe we should get the numbers from 0 to get a full octave, okay? And this is the way, with this formula, this is how we can turn any sound, any noise into music. And these numbers are precisely how MIDI numbers on your MIDI keyboards or on MIDI synthesizers work. It's the exact same thing. And here's the second thing about Snap that I'd like to show you. Now, this is a way where we can interact with, our surroundings. We take the microphone to record something. We can experiment with stuff. We can Google fun stories about Chinese princes and Dutch jacks of all trades. And then we can turn this into our own block. We can make a block that abstracts this. Snap is also called build your own block because we can now build a block. And I want to build a block in the sound category. We can make a new block. I want to make a block that uses my recording and plays it back as a note, as if I'm using a, play this note block. So I can say, play sound. Well, no, let's say play note. I'm going to want the input of the sound. So this is the block I want to make, maybe for n beats, right? Maybe I'm going to say note. I'm going to say pitch, whatever. So it's the note. Okay. So this is the block I want to make. So when I say, okay, I'm getting the new block. And now I can turn these into inputs. I can say the pitch is going to be an input. I can specify that it's going to be a number. I don't have to.
Be the input?
Excuse me?
Didn't you want note to be the input?
No, the page.
You saying play pitch was supposed to be text, I thought.
Oh, yeah. Brian just tells me I should make note the input. Okay. I can make, this is going to be a number. And the sound is also going to be an input, where I want to put in the sound. This can also be an input. I can make in Snap, I can also make a list of sounds. I can get it in here. I can say, I want to get a menu of the sounds. And I'm getting the sound names in here. And the third input is going to be the number of my beats, which is also going to be a number. I can put in here default values if I want. I could say for 1 beat or whatever. Then this is going to show up in the palette. But I don't have to do this. And so now, when I apply this, I'm already getting the block. Oh, wait. I said OK instead of apply. I'm already doing this. And the way we're teaching this in Snap is that we can now do like a little test melody. Let me actually, I should have prepared this, right? I should have a test melody somewhere. Elise. Yeah, I've got a test melody, which I stole from my friend Ludwig. It's a bunch of numbers from, let me actually try whether this works. So this is a melody. It's just a bunch of numbers. And these are low numbers, right? Let me now take this. And what I want is this formula, the 444,000. And instead of the numbers from 0 to 12, I want to get the note in here. This is the note that I want to do. So now I can do, okay, play the sound, any sound, for like at this pitch. And I want to rest for whichever beats I have. So now I've turned this into a block. I'm going to apply this. Now I've got my song, Elise. Was she his girlfriend? Anybody know? I don't know. Maybe.
Apparently it was mistranslated.
Oh, it was mistranslated.
It was not Elisa.
Oh, she wasn't a girl?
She wasn't Elisa.
Oh.
Someone
Oh, she wasn't Elise. Okay, good. Well, that happens. I mean, Beethoven also kind of was deaf like me, I guess. So maybe. Okay, so für Erich, okay. So we're going to play for each note. And für Elise, we're now playing this note. I'm playing the pitch note of my sound Snap. Oh, now I need to get the sound. I need to get the sound, right?
yeah. Something of sound. Oh, this is already a sound, isn't it?
Huh?
This is already a sound, isn't it?
Oh, it's already the sound. You're right. It's already in here. Yeah. Play sound Snap for 1 beat. Okay, let's try this. Okay, and this is how you can make music in Snap. So this is kind of, and if you, like if this is too high, you know, you can basically just make this lower, and this is. So you can use this to tune it so it fits together with other instruments or with other noises or sounds that your friends have recorded. So you can then make music together. So you tune this And then one can play Elise and the other can play für Erich, and you can see how it works together.
Maybe leave time so they can.
Exactly. If you'd like, try this. This is, in a nutshell, kind of two of the powerful ideas that we think make Snap special. We interact with the world around us. We can use sensors and record stuff and play it back. And we can experiment with algorithms and build them into blocks. So we can abstract them away, and now we have a new block, a block that makes music from things that we record ourselves. It's a function, right? So if you'd like to play with that, and if you'd like to know the notes that Ludwig wrote for Erich, here they are. This doesn't mean that you cannot do this in other programming languages. You can do this in most programming languages, but this is sort of, in essence, what we'd like computing to be. Something that lets you explore the world and bring a smile to the faces of your friends. This is one of the activities you're going to hear more about next year, because we're all working on a book of awesome algorithms. And this is sort of an introductory activity we're doing, which is then going to build up on how to manipulate media, how to turn this into actual ringtones on your phone. So we're going to do more things like how to playing it back at different speeds, but how to actually compute the numbers so we can put them all into a big list and export them as a waveform. But you can always build up from things. The main idea is this, that there's this formula that you can use to transform any noise into any music. And just with this little thing, I'd like to hand it over now to, I think it was Michael or Brian, to Brian,
Okay.
to show you what he thinks was the most special thing about Snap.
Okay. Sorry for being technically incompetent here. I'm different from Jens. It's a little scary following Jens because nobody does demos like Jens. And what I want to show is something really, really simple. And it's this. If I say 2 + 3 and I click on it, I get 5. If I put it in a ring and click on it, I get 2 + 3. This is the Lisp lambda. Take an expression and make a procedure out of it. Make it a function. What just happened?
Oh, right.
Oh. Fine, I agree to the terms of use. Woohoo. Every good programming language, which means every programming language except for Python, has lambda, has something like this. Those of you who've seen Python are thinking, wait, of course Python has lambda. But it doesn't. It has a messed up, stupid, incorrect, and anyway, because Guido von what's his name hates lambda passionately, but his users insisted on having lambda. And so he implemented the worst lambda he could possibly think of. But every other programming language these days has lambda. Even C has lambda. Even, if I'm remembering correctly, Microsoft Excel, right? They added lambda. So what makes Snap special? What makes Snap special is that you can see that the result of clicking on this is a block. If I had to explain to you what Lambda is with just text to look at, I would type in, LAMBDA, parentheses, close parentheses, blah, blah, blah. And maybe you'd understand it, and probably you wouldn't. And anyway, you'd be bored. If you look at this, you say, oh, wow, blocks are data. And the thing that makes Snap special, well, the thing that makes Snap special compared to Scratch is that it has Lambda altogether. The thing that makes Snap special compared to languages that aren't Scratch is that it has visual metaphors. That you look at what's happening on the screen and it teaches you something. So going along with that, let's see if this still works. It's been a while. Open. Examples. V. Yes. Oops, there we are. Okay, this is V. What it does is, if you look down at the bottom, it draws a V with decorations on the ends. You've probably seen this before because the way Snap got started back when it was BYOB was they made me come to a Scratch conference, kicking and screaming, because I said, what kind of programming language doesn't have procedures? And so while I was there, I organized a ad hoc off session about things you can do in Logo that you can't do in Scratch, and showed them V, which was invented by Paul Goldenberg to teach recursion. You'll see in a minute. And in the room, unbeknownst to me, was Jens. As I always say, the difference between me and Jens is that I'm a complainer, Jens is a doer. So I complained that Scratch didn't have the ability to make procedures. Jens went home and made it have the ability to have procedures, and that was BYOB. Okay, so if we click on the green flag, can you see, or am I totally in the way? I'm totally in the way.
And we can see.
Huh? Well, you can see because you're over there.
Oh, we can see.
And the folks online can see.
Folks online can see. But, but now the folks in the room can see. Maybe, except for you, right?
No.
Okay. We are so organized. The thing that makes Snap special is that we are totally organized. Okay, so I click on the green flag and we get a differently decorated V. It randomly chooses decorations. And now I say I'm teaching a class of kids about recursion. They've never seen recursion before. Now I say, oops. Okay, why isn't this? There we go. What happens if I add V to the list of decorations? What do you think happens? Okay, class, take out a piece of scrap paper and then just scribble a picture of what's going to happen if it chooses V. And then we click on the green flag and nothing happens special. And then this happens. You guys all know about recursion, but the hypothetical kids in this class have never seen it before, and the entire class gasps. How did this happen? There's nothing in the code. The code is just turn left, move up, draw a decoration, come back, turn right, move up, draw a randomly chosen decoration, move back, and go back to the starting position and heading. And yet somehow it managed to draw this amazingly complicated thing. And I can keep going. Oh, whoops, nothing much. Oh, that's interesting. If we keep going long enough, eventually,
Yeah.
it's going to fill up the entire screen. It's going to go crazy. Maybe not. Yes, yes, and you'll notice that I added 2 V's instead of 1, and that's why. I'm cheating a little bit and by making it more likely that it's going to choose to recur rather than have a terminal picture. So that's the lesson of V. As I said, invented by Paul Goldenberg in Logo before some of you were born. But the other thing about this, that when I'm talking to teachers rather than kids, I say, look at this. Have you ever seen something like this before? No. But you've seen lists before, and you've seen blocks before. So you look at it, and without me saying a word, you know that this is a list of blocks. And so this abstruse, complicated, kids couldn't possibly understand this, we shouldn't have it in the curriculum idea becomes trivial. Because you can look at this picture, and the picture is worth way more than 1,000 words in trying to explain first-class procedures. This is what's special about SNAP. Yeah.
If you hide the hieratic mysteries, people will realize they're not listening.
Sorry?
If you hide the hieratic mysteries, all the people will be able to do.
Oh, yeah.
We can't have.
Oh, right. Yeah. It's true that recursion is sort of a great divide among programmers, right? They're the ones who get it and the ones who don't. And the ones who get it can still get jobs. Okay, that's it. That's my demo.
I'm going to do a quick demo of things that I do in Snap 11 and why Snap is awesome. This is not specific to Snap, but before I do that, because Brian mentioned V, to further show why Snap is awesome, I teach, or one of the courses I teach is our intro computer science course for data science students in Python. But because I teach the course, I can't resist bringing in some of these things into teaching about recursion. So this is my version of V in Python, which largely works the same way. Like you can hit the up and down arrow keys to add functions to the list. And to their credit, higher order functions in Python have kind of nice. You just don't use the parentheses to get a function. But like visualizing a function in Python is this track. Function V at some address thing. And I guess because these numbers are like the same thing, well, I guess that seems the same thing. And if I press the space key, like I get a bunch of hopefully interesting V's. And so the demo does work, and you can teach these things. But I do really think this idea that, and I have a little slow, so animates. If you are doing this, a little bit of animation class. This is probably a little slow. Helps build the effect of if you're crazy. And because I teach a data science class, in many ways, I will say this is like a fun introduction to recursion. Because the base case is implicit, it's some ways not the easiest way to teach recursion, but it leads to great discussion of statistics and probability and when will like recursion eventually end or not end. So again, Snap is awesome, even though I'm showing a Python thing right now, because the V demo on Snap just looks like infinitely better than the one that's in Python. So what I wanted to actually show is something that is kind of new in Snap 11, but actually I think something that at the same time wasn't, didn't require any of the new features necessarily. Snap 11, we just made it easier. And that's first class colors. And the reason why I think it's cool in Snap 11 is because, and I'll make this, let's say, we'll go zoom blocks, I'll make it, let's do 2.5, will be slightly bigger. So we have a color and we can do things like, if you happen to know about how colors work, you can pass in values for these things. And if I pass in 3 values, it happens to turn out that this thing is red, green, and blue, and it's RGB color. And that's not the most discoverable thing. There is this nice other color block, which exists over here, that will give you, a different range of colors based on hues. And if I put in 50, I get blue. And one of the things that I think is super cool about colors, the same way that you can do this with sounds and various forms of media, is using this to just start to explore, how do things work. So, I'm used to at this point the scale of RGB colors. I spent enough time working with them that I have a sense of what's there. We can talk about why this value is 25 in a moment, because obviously 25 is meaningful to this. But if I just click map, in this case, what do I get back? I get back a gradient of colors from light to dark, and they're all red. And a good thing that I can see is like, well, all right, what happens if I move this to another spot? Now they're blue, and now just by like playing around, I can sort of start to get a sense. Well, okay, this first thing, I already said it's RGB, but if we didn't know, right, we could start to easily play around and figure these things out. So I like starting or talking with students about RGB because for those who have an art, photography, Photoshop, whatever background, or maybe a little bit of web design, they're seeing RGB colors. If you're in an environment where you have to teach things like number representation and binary to decimal, this is a good introduction to the one place where like reading hexadecimal values is actually pretty commonplace in in a field. Whether or not it needs to be that way is a different question. Yes.
There's no such thing as converting binary to decimal.
Oh, yeah.
And if you go to the Snap forum under blogs, is that where it is? You can find my rant about why there's no such thing as converting binary to decimal, or vice versa. Carry on.
But there's this other block called hue, and one thing that you might notice is that like the default values, if I expand this out. Also, actually, we kind of skipped over this. I assume people at Snap can know this, but since this is going to be recorded, what actually makes Snap awesome compared to everything else? Default arguments in functions don't have to all be at the end of the function. So if I have hue, part of my block syntax and name can be a block which is new color hue that takes in a hue of 50, a saturation of 100, and I can just like interleave names and arguments. We all intuitively know this is awesome. I will say that even like as a Snap person building curriculum and projects, it is very easy to forget that you can put words in between your parameters, and you should do that because, like, again, this is 100 times better than putting 3 numbers at the end of a function call in Python. But anyway, so now I have this thing called hue, another way of making colors, and the question might be like, well, I don't know. I did 25 before. I have these three values. I still want 10 values back. Well, that's interesting. We have a green, we have a cyan, a blue, a red, and then a green. 25 is kind of an interesting value. What if I, let's say, want 10 distinct colors? What value maybe should go in this multiplication block? Someone suggest a number that I could just try. Whether or not it's right or wrong. 25,
Are you looking for 25 and a half?
25 and a half?
Yeah.
Well, we could try that. I mean, we get most of the same posts, slightly different though.
Yeah.
Anyone want to shout out a number? What should I try? 1,000. 1,000. That's a good idea. All red. Interesting. Ooh, what does that suggest? Maybe. Yeah. No.
Well, 1,000 is divisible by 100, and the hues are inside 100, and so and red, the 100 is equal to the 1.
All right. Cool. So you already know what the scale is, which you said is 100. So we could try, something like that. But this also illustrates a good point. What if I try just 100 here, still red? And you're right, because we're multiplying by the same value. So this suggests maybe something like 10 would now give us 10 distinct values. And what I really liked about things in Snap is that this is, to me, a fun combination of playing with data, but also playing with a simple map, higher function. And one thing I did just as I was sitting here is like, okay, I was just plugging numbers, into a block of playground. And I think a little bit of complexity I'm working with students, can help here, which is saying, all right, what are the things that I'm really trying to manipulate in this case? Well, it's something like a max value. And what I like about declaring, again, another useful thing, script variables not specific to Snap at all, but what the hell is the scope? What on earth is the scope of this script variable here compared to this script variable here? Well, the nice thing is like in Snap, we're just if it's below this gray thing, this max value, could be right here.
Wait.
Yeah.
Now, please, I'm sorry to hijack this. Please click on the debug button on the step button.
Right?
No, yeah, no, the one with the footsteps.
Oh, yes.
And now hover over, and you can see the scope of the variables.
Oh.
If you're in debug mode, you can visualize. And now if you go and hover over any of these, you can see where they're actually declared. So you can explore the scope of variables in Snap. So because y'all are teachers and you're all complaining about, oh, there's no way to debug blocks languages. There totally is. Okay, sorry to hide.
I mean, if you do teach languages like Python or JavaScript, the amount of software that is also written to like make these things, more visualizable. But the nice thing is that like I can start to do things. What if I'm trying to understand, the saturation value? I can, manipulate this. And I put here the max value is 100, and I want to see 20 colors. But what if I'm not sure? Like a good question here is like why? And if you've used another program to learn color, so I'm going to go back to the hue example in the middle here. You've probably seen things like a color wheel that has 360 degrees because it's a circle, and so your intuitive guess might be something like 360. And it turns out that we normalize everything to 100. You'll find it's 100 in lots of places. I could try things like, what if I want more colors? That still doesn't work. And so one thing that, if you set this up, you can see students is, all right, 360 still gets, some repetition. Maybe I drop it down to 200. I still get some repetition. Maybe I try like 20, and now I don't see some of those same colors. And you could start to, just work with students and say, all right, try some colors till you find that right value. And it's not this way, but if you really wanted to, you could say, well, if you try 360, you get too many colors, and you try 10 or 20, and you get too few colors. How do you find out what value to try next? Maybe that leads into another discussion of another simple but awesome algorithm, which could be binary search. And there's a lot of ways in which you could, I think, just simply taking map a couple lists and start playing with them. So that's why I think Snap is awesome, because I think playing around with things is really fun. I'm going to share, and then Brian can let you go.
No, I want to talk about what you just said.
Yeah.
There's a subtle point here, which is that hue numbers wrap around. So whatever the maximum value is, it isn't really the maximum. You can have any number, but 101 is the same as 1, right? And that's not an obvious thing. Kids may not get it, so it needs to be talked about.
That's true. And if you're in a math class, that could be a good discussion for modulus.
Yeah.
If you really want to. But the thing that I was going to show, and I'll pull this up on the Snap Cloud because I didn't open it for some reason. It should be. This is the fun thing about
No.
nope, if I type the word final correctly. I will add this to the 6C collection. So I did some of this stuff before Snap V11, where I had to hack around colors. But one thing that I want to show is just when you start to do things like meeting, and I believe this one has the solutions. You can start to, let's say, actually teach kids about, well, what if I were to make, in this case, you had to do things through costume. What if I want to make very specific colors? And I could do things like, well, maybe I should display the original image. So let's do, no, I need to do one there to display the original. What if I wanted to take these same types of colors and just start multiplying images? So I have a picture of a building in Berkeley. And what if I try and make this gray pixel and I start multiplying the colors of the pixel by various amounts of gray, and you can start to see that in this case it just gets increasingly darker. And I'm going through this in like a couple of minutes, but I think that's the power of media computation Snap. If you want to try and do this in another language, especially a text-based one, then you have to deal with files and all that stuff on a computer. And it turns out to just be so much code that students either run into errors or they lose track of things. So I think map colors, we did a section a few years ago about like map is all you need as a block. That's why I think Snap is awesome. So I'll put these in the Snap Cloud collection. But that's another really fun and simple thing that you could do with just messing with, really underlying this block here is just a couple simple expressions.
Okay, so I want to go back a couple of steps from what Michael showed. I want to talk about hyperblocks, which is one of the things that I love the most about Snap. And I want to show you the basics of hyperblocks up until the point where we can start modifying pictures and, making them darker or brighter or applying different effects with just super basic, super simple arithmetic that we can all understand. Is this too small? It's probably too small, right? Is this better? Okay, wait. It's better, but not perfect. Now it's perfect. Okay. So let's say we have a list of numbers. I'll make it 145 minus 4, 98, 4. And I want to apply an operation to each one of these numbers. Okay, I want to add 10 to each one of these numbers. In an imperative programming language, what you would do is you would, well, you want me to do it, it's painful, but I can do it. It's really painful. So say this was some other language, I would have to have an index. I would have to set the index to be 1 so as to point to the first element in the list. I would have to say, this is very boring, repeat. I would have to have a list, actually a list variable where I store this thing. I would have to repeat the length of this list. I would have to have another list, new list. See, I'm being make thing like a computer, and I don't like thinking like a computer. So in this new list, what I'm going to do as many times is I'm going to add the item. I hope you're seeing how boring this is. That was the intention. The item index of the original list to the new list. Only this time I'm going to apply an operation to it, for example, adding 10. And I can't forget to change my index by 1 at every step. And now I've added 10 to each one of the items in the original list. Okay, this is obviously very verbose. This is making you think like a computer, thinking of indices, thinking of temporary list, thinking of taking care of the length of your list, whatever. This is prone to so many errors, and this is knowledge that's not really interesting to humans. It may be to computers. So
I think it's good to see that you can sort of tell the literature some programmers that they're old enough to apply Fortran, so they can write Fortran in any programming language.
yes, yes, exactly. But thankfully, we've invented a bunch of languages after that. So I'll show you what.
Even Fortran has Lambda now.
Yes. So there's a slight modification that we can do to this, that we can apply to this code. If we have something like for each block in our language, for each is a loop that takes in a list and iterates over each item. So what it's doing is basically helping us get rid of the index thing and the length of thing. So we get rid of 2 variables, that's good. So we still have our list and our new list, and we just say for each item in list, add this to new list, okay? Hopefully you see how this got slightly better. No, what did I do?
Not item index.
Oh, sorry, add item plus 10 to the new list, right? So we got rid of the index. This is much more readable. This is much more understandable. It's thinking a little bit more as humans do, a little bit less like computers do, and it does the same thing. If we look at the new list, it now has the items plus 10, but it's still not thinking like humans do. The core question was, what does this list plus 10 look like, right? And the answer was, well, given a list that has these items, given a new list that's empty, for each item in that list, that first list that I told you about, add the current item plus 10. This is not what I was asking you for. I was asking you to add 10 to each item. It's still thinking as a computer, maybe a more advanced computer, more human-like computer, but it's still thinking like a computer. So that's when functional programming makes things more readable and more human-like, more higher level. Map is a block, is a function that takes in a list and applies an operation to each one of their items. So it abstracts away all of these processes, okay? So I can basically throw away all of this stuff. I have my list, and I want to do something to each one of the items of this list. I want to apply some operation. Which operation? In this case, it was the +10 operation. And this looks much more like what I was asking for. I was telling you to add 10 to each item on a list. So I was asking you to map the +10 operation over this list. This is much more the way that humans think. And one other advantage to this is that now we can see where the transformation is happening very clearly, because we got rid of all the craft about indices and items and whatever. So now it's very clear. We have a list and an operation, and it's very easy to change this operation. And it's very easy to change this list. We could now have a list of Mary, Jane, Peter, Anne, and map something else over it, like, I don't know, join hello. Let me get rid of this. So we've map abstracted away all this process of dealing with lists and applying operations to each one of their items. Okay, up to here, this is functional. This is what a functional programming environment provides to you. Then in Snap 9, I think, or 8, around that time, we realized that when asked this question, some kids and some adults who were not programmers by craft would say, why can't I just do this? This is what you're asking, right? You're telling me I have a list and I want to add 10 to it. And then we went on to say, no, wait, there's a misunderstanding here. This is a list, this is a scalar, this is a number. You can't add a number to a list. These are two different types. These are two different dimensions, right? This is a one-dimensional element, and this is a zero-dimensional element. But you asked me to add 10 to a list. Why doesn't it do what I'm telling it to do? Why is it giving me an error? And in the end, well, Jens decided to actually implement what users were thinking that this should be doing. And this was based on other programming languages from the past that actually worked like this, namely APL. And actually, this is now the way that you can add 10 to a list. You can obviously do the same thing with join. So you can join hello and a list. Oh, sorry. No, not this way. Not with join. Yes. That was the wrong example. I should have prepared. But okay, now that we can apply an operation to a list, we can start to see how this translates into what Michael was showing before. Because honestly, yes. Oh, I have an actual physical, what was it, security client? And now I have a picture. And as you've probably seen before in Snap, as Jens was showing before, any media object in Snap is represented as a list. A sound is represented as a list of samples. A picture is represented as a list of pixels. So I can ask for the pixels of this current costume, and I get a list. Technically, it's a list of lists. That still doesn't disprove my point. It's still a list. So I should be able to add something to it. I should be able to apply a hyper operation to it, such as +10. So let's see what happens if I get the pixels of the costume and I add 10 to them. I don't know if you remember the original ones. Let's actually keep those here and add 10 to them here. And as you can see, Snap smartly added 10 to each element of each list, okay? So hyper operations sort of ramify, is that a word? not
It
really.
is a word.
It is a word.
I don't know if it's what you mean or not.
Branch out to every element of its list until they reach an atom, or until they reach something that has the same dimension of what we've tried to add to, if that makes any sense. So it basically tries to match the dimensions of what you're adding, and if they don't match, it finds the most obvious way to match them. Does that make sense? Hopefully. Okay. So what does this look like? What does this look like, adding 10 to a list of pixels? Let's switch to that costume. And suddenly, it was not very noticeable. Did you see how it got slightly brighter? Let's add 100 to it. Now it's much more noticeable. So this is a way how you can start to experiment with graphic effects in Snap with very basic arithmetic. You can try crazy things. Let's take the square root of my, and as I said, this was completely unprepared, so I don't really know what's going to happen. I'll probably have to multiply this by something, because square root gives small numbers. Let's say 20. That didn't do anything. Let's try something else. Let's try someone. Tangent. Tangent is a good one. We'll try sine next. 300. Right? Random numbers. Yes. Sine. What does sine give us? Sine. Sine is not going to work. Yeah.
Because you still got the algorithm, so you go to the right extension, it's nice.
Yeah, exactly. Exactly. Well, you can do other things with this. Let's take another picture. I'm leaning the other way intentionally. And now let's, since these are two lists of numbers, right? And I said that you can add things of any dimensions. Can I add the pixels of one of the costumes plus the pixels of the other? Yes, of course I can. I get very big numbers, but we'll see what happens with this, right? Let's switch to this costume and see what happens. Did I do that right? Oh, I was leaning the same way. Okay, because it's mirrored, of course. Okay, so I have to lean that way? Is that what it means?
No, the other way, huh?
No, because it mirrors.
Oh, yeah, you're right.
That's why I was tricked before. There we go.
There you go.
So it mixed the two pictures together. Of course, all over the place, because we're getting very high values because we're adding two pictures together. So if we want to actually have them be mixed in a more tempered way, we can divide those values by 2. And now we have sort of the same light values as we had in the beginning. So we're basically getting the average of 2 images with just simple arithmetic operations. And again, nothing stops us from doing this with live video. I don't know, how are we with time? We have 5 minutes. I think we can do that. Again, this is unprepared, so it might not work at all. But let me start by switching the camera on. I went to sensing and clicked on set video capture to true. So I'm now seeing myself live in here. And what I want to do is I want to get my feed, my camera feed. So that's the video snap on the stage. Let me get rid of this stuff. This is a very slow computer, by the way, so things might not work as well as they will in your computer or Jens's computer. That's a space rocket. So what I'm doing now is it doesn't make much sense. We were already seeing my video here, and now I'm just switching to the costume of the video snap on the stage. So I'm basically doing the same thing. But now I can do things to this. For example, the tangent thing. Was 300 the magic number? So it's the tangent of the video times 300. Is that it? Oh, of the pixels. Yeah, sorry. Have to get the pixels of the video snap.
Yeah.
At the tangent, and there you go. Okay, you know, oh, it's nice that it's actually picking
It's
me from the.
yeah, the middle. The middle.
So we got a
Recursive.
recursive me.
Right.
Okay, I think that's all that I wanted to show. I'm leaving this up in case you wanna. But as you see, media computation in Snap, thanks to Hyperblock, has gotten that simple. Just applying arithmetic operations to lists. We don't really care about the dimensionality of these lists. They could be 35 dimensions for all we care. It just works. We have a bunch of effects that we've discovered with time. Things like, one of my favorite was the drunk cam effect that kept superimposing the last frame with the next one. And then when you move, things go like slowly, you know. Well, I think that's all. I'll leave it here. And I think that's all for all of us, right?
Yes.
Yes. Excellent.
Questions?
Any questions or comments or complaints?
I just think it's really cool the way you can take the list operations and you don't have to indoctrinate people into thinking like a computer before they can do things.
Yes.
Because once you've taught them that, that's how they will want to do it forever.
Yeah.
So what's the thing? I have to go through the list one by one. Even in languages where they can operate on the whole list, they'll still do it that way. I have colleagues who have been teaching Fortran for a long time, then we switched to MATLAB, which has all this array processing built in, but they still wrote programs that went through each element of the array.
Yes.
Right.
That's why it's important that we show these things, because otherwise people will teach Snap the way they teach other languages, and then they'll be like, what's the point of using Snap? I can do the same thing. Yeah, you can do the same thing as in another language, but this you can't do in your other language. So this is the way we should be teaching Snap.
I enjoy the fact that you change something to adapt to user habits. For example, when you try to do that operation with list, if I am a mathematician, I would not change it because it is like the operation is list and is a number, and you cannot put together. But
Yep.
I like the fact that you edit this to make more user friendly.
This happened a bunch of times in Snap. Like,
So the point is, you're a mathematician. It's actually for mathematicians that we added it, because it is vector and matrix operations.
No,
So
but-
the pairing is exactly the way how it is, like when you're adding two vectors, or when you're adding a scalar to two vectors. And one reason that we're using this for media computation is that this is a very accessible way to experiment with media to get immediate feedback. But the deeper kind of reasoning behind this is that it's another way to look at clusters of data. So it's clusters as we find objects, or that we find in many of the applications of computers right now. Something we're going to show you tomorrow, like neural networks, like AI, which all, if you get lost in iterating through the items of several lists and aligning them and pairing them up, you get lost. Like you don't see what's behind this. And so this is a point. So real mathematicians will object that it's only part of that. This isn't the complete linear algebra. It's only the pairing, only the component-wise application of an operation. So if you want to have the inner product, of a matrix multiplication, you still need to write that yourself. You need to take, you need to do the component-wise multiplication and then do a sum, for example. And there's other words that we build in. For example, if the two vectors don't fit, we don't give an error as real mathematicians do. We just cut into the ones that fit, which is great for media because you can use it then sort of as a mass and you can do nice things. And it's also what people in AI, I believe. It's what you do when you do neural network and you kind of reach over the edge of one of the matrices. You do what they call a zero padding, for example. So it's in essence that makes.
But I think Bea's point was that she finds it nice that when users do something that gives out an error,
Yeah.
we think, well, should that be an error?
Yes.
And maybe it should not. So
Like if we show an error, and we've sort of taken this as a design maxim. If we show an error, we think twice because maybe the learner meant something that actually
that we hadn't thought of.
and we should maybe do what they meant.
Maybe they're smarter than the computer, and we should listen.
Well, that-
In my professional